Our next speaker is Costanza Benassi from Northumbria University. And Costanza will be talking about random matrix models, integrable lattices, and thermodynamic limit. Thank you, Costanza. And these talks might be on slightly different topics than what we've seen last week and today so far. I hope to be as introductory as reasonably possible. So I hope I can start. Great. So, the focus on this talk is on random matrix models and the relationship with integrable hierarchies and the thermodynamic limit. And I do realize there are a lot of words here. So the first thing I want to do is to try and explain briefly what I mean with these words before we actually go. People continue on it. Okay, great. So first of all, let's try and understand what all of these means. So random matrix model, very, very briefly. So random matrix models can be found everywhere, in physics, in mathematics, and they link many different fields together, from integrable systems to QFT to statistical mechanics, which is my original background. And the idea is that we can define them as probability distribution over a suitable space of matrices, of square matrices. And usually the form that we have in mind is something that resembles, I'm not sure how, okay, that resembles, for those who are familiar with statistical mechanics, a Gibbs weight. So the probability of a symmetric matrix will be proportional to the exponential of some potential, and this potential usually depends just on the traces of the matrices involved. Okay, so this is the general setting. And we're going to look at cases where this potential is actually polynomial. All right. And Z here is just a normalization constant that ensure that this measure, well, is actually a measure, so that it integrates to 1. And this Z is the partition function. So the models that we have in mind usually have a potential of this form. So you would have, as I was saying, a polynomial. Usually we fix a coefficient for the m squared term, 1/2 m squared, but then basically we sort of modify it slightly, we deform it slightly by introducing sum of powers. And these here are parameters that I can play around and modify and see what happens to the model, basically. And for the time being, I'm going to call them coupling constants. Your partition function then takes this form. And of course, what do I have here? Well, depends on which set of matrices I'm looking at, right? So in particular, we'll be interested on the HME, which is the set of all n times n Hermitian matrices. And these will be based on work in collaboration with Antonio Moro, who's over there. And we're also interested in what is called the SME. So the case where we're looking at symmetric matrices. And this is based on joint work with Antonio and M.Dell'Atti, and they're both, again, in the room. And why am I so interested in the partition function? I'm interested in the partition function because, well, if I take logarithmic derivatives of it, I basically get the momenta of my distribution. So if I'm interested in understanding what happens to this model for different values of t, of the coupling constants, basically studying the partition function should give me the ingredients I need to understand what's happening, all right? So this is exactly what I'm interested in understanding what happens while I tune these parameters ti, okay? And I'm going to use some ingredients, specifically the relationship that's very well established between these matrix ensembles and some integrable hierarchies, some lattice integrable systems. And I'm interested in what we call the thermodynamic limit. So what happens when the size of your matrices get bigger and bigger? And that's usually when, interesting behavior comes up. And what we're interested in is phase transition, which here I'm going to be very vaguely defining as some sudden change in the phenomenology of the system. And we hope that we will be able to detect these sudden changes by studying the partition function. So I'm going to restrict myself to a slightly less general case, but it's actually very interesting on its own. So in the case where our potential has only even degrees of interaction only. So here, instead of having any possible power, I'm just going to have even powers, okay? And I'm going to exploit a very well-known fact, that is that given that our potential here depends just on traces, it means that I can write it only with the eigenvalues, using the eigenvalues, and I can recast this all z just as an integral over the eigenvalue times an irrelevant constant, okay? And this is a very well-known result in the literature, and the idea is that basically you can recast z in this form here, where you have a van der Monde determinant to some power. The power depends on the matrix ensemble you're looking at. It would be 1 for SME, so symmetric matrices, and 2 for HME, Hermitian matrices. And then you have this product here that basically just reproduces the form of the potential that you had for the matrices, all right? So Z is proportional to this integral here that I've called the tau, and I've not called it tau just out of a whimsy. We're going to see in a second that there's a reason I'm calling it tau. And there's going to be some constant here, which is not really relevant. That basically is where we've put everything that's a degree of freedom that's not our eigenvalues in our integral, right? So from now on, I'm going to refer to tau mainly instead of Z. But when I talk about tau, you can think of it as your partition function, basically. Nothing has changed. I've just recast it in a more convenient formulation. Okay? I hope so far so good. So this was very fast. I'm aware of that. So let's start with the first case. That is when the matrices we're looking at are Hermitian. The fact they're Hermitian means that here we have a 2 in the van der Monde determinant. And this is the newly cast partition function we're going to look at. So now it's going to look like I'm going to do something that doesn't have anything to do with what I've been talking about before, but it actually does. So let me define a semi-infinite operator L, which is just symmetric, and it has only the upper and lower diagonal with non-zero elements. And these elements I'm going to call B1, B2, B3, and so on and so forth. And this Bn I'm defining as actually being given as the square root of a certain ratio of taus, okay? So these Bn's are just tau n plus 1, tau n minus 1 divided by tau n squared, all under a square root. You could think, so these Bn's here depend on n, so depending where you are along your diagonal, and on the coupling constants that are hidden in the tau. And based on a theorem by Adler and Van Merbeke, it's very well known that this semi-infinite operator is actually the Lux operator for the Toda hierarchy. In this case, it's the Toda hierarchy restricted to even times only. So it just means that L satisfies this specific differential identity. Okay? Where here T to K are exactly the coupling constants that I have hidden here. And here by skew I mean the skew symmetric part of L, and this is just a standard commutator. So this is not the general Toda hierarchy, as I was mentioning, is the Toda hierarchy restricted to even times only, because we're taking even powers only in our potential. And that is also known as Volterra hierarchy. So end of the day, tau n is a tau function for the Toda hierarchy. So that's why I called it tau. It was not just, randomly chosen. So what does this mean for our B's? At the end of the day, I'm interested in our B because these B's are the ones that have to do with our partition functions, which is what I'm interested in, right? So this is just a very silly example to show what happens with the first equation of the hierarchy, which is T2, the one for the first coupling constant. Basically, you can define L square, and you do it with Mathematica, and it's super easy to check that it has this form. Its skew-symmetric path will look something like this. And then you just need to check that these two things need to be the same according to this differential identity. And then you find the general form for the evolution of your Bn. So you can think of your Bn basically as fields living on a lattice, on a one-dimensional lattice, and that evolve in this time T2. And there also, of course, there's going to be infinite flows because of these integrable hierarchies, one for each coupling constant. So the coupling constants play the role of the times of the hierarchy. And of course, there are infinitely many solutions of this hierarchy, but we are interested in the one that's consistent with the form that we have for our partition function, for our tau. And it is specified by this specific initial condition. This can be calculated quite quickly because these tau are just Hilbert integrals, basically when you put all coupling constants to 0. Okay? So it looks like we're in good shape because this B here evolves according to a very well-known hierarchy, and we know which sort of initial condition we have in mind. And actually, we can generalize it to any flow. Okay, so we know how to construct the equation for any flow at this point. I'm just going to switch from this small b to this capital B. There is just a square in between, so I get rid of that annoying square root that I had at the beginning. So my capital B is just this ratio. And I'm going to interpret this capital B as the order parameter of the Emission matrix model. By that, I mean that I'm going to try and understand how this one behaves in terms of the coupling constants. So in terms of this evolution at the end of the day, it can be shown that this evolution has this form where V is a suitable combination of the Bn, and this V is going to be different for each flow, of course. And it gets worse and worse as you go to higher and higher flows, but that's sort of to be expected. Okay, but the point is that we have basically a recipe, an algorithm to find this V for any K. Okay, so if you want to write the whatever flow, you can do that. It's going to look more and more complex, but that's the way it is. And we can say, based on results on the total lattice, so on the case where you have all times, that also in the case where you have only even times, we have actually an explicit solution to this hierarchy with this specific initial condition, which is given by this. So of course, this is in recursive form, is implicitly given, because these V's, as I mentioned before, are certain specific combinations of the B's, okay? So you have B here and B is here, and so all this is going to give you a big recursive equation, but still it's an explicit solution. And this is actually a generalization of the string equation result by Jurkiewicz in 1991. To actually take a look explicitly at this solution, from now on, I'm going to keep only the times T2, T4, and T6. And I'm calling them times or coupling constants independently at this point. We'll know that it's the same stuff. And I'm going to put all other times to 0. Okay, so I can actually take a closer look at this solution. But as I was mentioning, interesting things happen when we take the limit for n that goes to infinity. And specifically, what we have in mind is that the thermodynamic limit for the Hermitian matrix model would correspond to the continuum limit of the Toda hierarchy. Okay, so what I'm going to do is that I'm going to interpret the continuum limit of the Toda hierarchy as the thermodynamic limit of the HME. So how do we do that? We set a large integer, capital N, which basically defines our scale, and epsilon will be 1 over n, and then area scale everything appropriately. Okay, so I'm going to just define UN, which is a rescaled order parameter. Capital T are just rescaled times, and so on. Under this rescaling, if I take the continuum limit, so I take the continuum limit for U as epsilon gets smaller and smaller, and I call U the continuous function that I get, then this recursive equation becomes basically just a cubic in U with, well, the coefficients depending on the times. And here X would be the continuum limit for our discrete field, or discrete lattice parameter N. All right. So I'm moving from N to X and from B to U when I'm doing this continuum limit. And I just find a cubic. And this cubic, if you do the same game, but on the original differential identity instead than on the solution, is at leading order just the Hopf equation, plus some order 2 corrections here that we know how to write down explicitly. So the point is that we know that the Hopf hierarchy, that the Hopf equation develops singularities, all right? And indeed, we have a cubic equation which is gonna develop a singularity for certain values of the parameters involved. And in general, in statistical mechanics, when you have singularities of the order parameter, you have phase transitions. In classical statistical mechanics, these phase transitions are resolved by classical shocks. But in this specific scenario, we see something that actually looks way more like a dispersive shock. So you see here, what am I plotting? I have X and U, so X, U in all plots. I fixed T2, T and T4, and each picture is just evolving in T6. So you can think of it as a cartoon if you want. So I'm plotting on the dotted line the cubic, and in the continuous line, the rescaled solution to a recursive equation. So you see what happens when there is no singularity, no gradient catastrophe, everything looks fine, it's smooth and you know, reasonably nice. But then once that we actually go through the gradient catastrophe, we have this dispersive shock appearing. All right. So this is quite interesting per se, because as I was saying, in statistical mechanics, usually we find classic shock, not dispersive shocks. And so what we've shown actually that within the HME, we have a novel type of phase transition, which is signaled by the appearance of a dispersive shock wave. And you have to think of this dispersive shock wave as actually an object that lives in the space of coupling constants. So here I'm evolving it in T6, but here I have different parameters at play. I have T2, T4, T6, X, and so on. So actually, this is a sort of a multi-dimensional object that we need to study now. And that's what we're trying to do. That's basically what we're working on right now. Okay? So this is very briefly what I wanted to tell you on the HME. And now I'm going to move to the SME. And our scheme of thought is going to be pretty much the same. So I'm going to explore the fact that there is an integrable hierarchy underlying this model and play around with it a bit by doing the thermodynamic limit. Okay? So the difference here, which seems trivial, but it's actually crucial, is that in the definition of the partition function, we have the van der Monde determinant power 1 instead of having it power 2 as we had before. And this is going to make all the difference in the world. So we're going to play the same game as before, but it's going to be way more complex. So in this case, I'm going to define a lower triangular matrix, well, which has also the first upper the diagonal, but all the rest from here onwards is 0. And so let's start from the upper diagonal, which is the easiest case. These fields here, W01, W02, W03, are a combination of the taus that look very much as the BNs that we had before. So we have a ratio of taus on the rest square root. And you can think of this 1, 2, 3, 4, 5 as basically, again, your lattice size, okay? So the spatial parameter on a one-dimensional lattice. But the point is that we don't have just this type of field, W0, but we have different type of fields. We have other fields that we call W-1, or other fields that we call W1, and so on and so forth. And each of them lives on the same one-dimensional lattice. So the lower index determines where you are on the one-dimensional lattice. The upper index determines which field you are, basically, okay? And this W, again, can be defined as suitable combination of taus and their derivatives. And this WK, we're going to have infinitely many fields, because this K can, you can show that it can take any value, negative and positive integer. These infinite fields play the role of that B played before, but before we had just one, and now we have infinitely many. And you might be wondering, why are you building such a matrix? Because it turns out that this matrix is actually the Lux operator for the what is called the FAF hierarchy. The FAF hierarchy is a bit more complex than what we had for the TODA hierarchy, in such that here, before we had the skew, just the skew symmetric part of the operator. Here we have something that is way more complex, and I'm not going to go into it, but it's basically a projection of thought that is well defined, and we know how to do that. So all these you can basically calculate. Okay. So again, this is an integrable hierarchy. We have infinitely many commuting flows, one for each time. So watch for one for each coupling constants that again are hidden in here in the taus. And so tau is just a tau function for the FAF hierarchy, again restricted to even times only. This result holds in more generality for the full FAF hierarchy if you take both even and odd powers in the tau function. So don't be scared. This is just to give you a flavor of how they look like, and just to make you see that in this is more complicated than what we had before. I'm not going to go through the same example as we did for the Hermitian matrix model, because you can see from here that it would take more than a slide, and I'm not sure how helpful it would be. But the point is that exactly as we did for the TODA hierarchy, we have explicit equations for the fields as well, and they are in this form here. Okay. And again, of course, this hierarchy has infinitely many solutions, but we're interested in the solution which has this specific initial condition here. All right. And of course, we're going to need also initial condition on the other fields. But again, the game that we're playing is the same. I want to look at what happens in the thermodynamic limit. So in the limit where the sizes of our matrices goes to infinity. And so to do that, we're going to take a look at the continuum limit of the FAF hierarchy. And exactly as we did before, I'm going to set a large integer n, capital N, which just sets the scale. So epsilon is going to be our small parameter going to 0. And I rescale my time appropriately. And I define basically a continuum limit. Well, now we'll have a continuum limit function if you want for each field, and I have infinitely many, right? And the point is that if you do this, so you proceed with the same scheme of thought that we had for the HME, what you find is that, well, you have actually infinitely many evolution equations for each time. And that, of course, makes sense. You have infinitely many fields. So this would be the identity that you have for fields UK, where K is negative, U0, U1, and UK for K positive. And this looks bad if you look at it just, at a glimpse, but it is actually very nice. It's actually very nice because if you take a closer look at it, the equation in the previous slide have a very nice compact form, in the sense that the evolution in time of each field depends on the evolution in space of just a handful of fields. Basically, U0, U1, and then the previous one, K minus 1, and the following one, K plus 1. So it's actually way more compact than it looks from just the expression that I showed you before. And of course, here you have these coefficients, but these coefficients are going to depend, if you go back to the equations, just to a finite number of fields as before, typically the neighboring ones on U0 and U1. So we can actually write it in a more compact form, in this matrix form. So here U would be this infinite vector of fields from minus infinity to infinity. And A would be basically the matrix of these coefficients that I have here. And so you can just write it in this compact form. And what we have is that this is what is technically called an infinite chain. And you can see that this is a system of quasi-linear PDE of hydrodynamic type. So what we have is that we have a chain of PDEs, where before we just had one PDE for each time. Now for each time, we actually have an infinite chain. So you see how the SME is way more complex than the HME. And notice that U0 and U1 play a special role because they appear in the evolution of all other fields, which is not true for any other. So we call them seeds of the chain. And this is sort of special because usually when you have an infinite chain of quasi-linear PDEs, prototypical example being the Benny chain, you only have one field like that plays this special role. But here we have two. So the point is, the main point that I want to make is that we managed to prove that this chain is actually integrable. The whole point is, what does it integrable mean in this context? All right, so we're going to use the definition by Ferapontov and Marshall from 2007, that basically an hydrodynamic chain is integrable if for any integer n, we can find n-phase solution of this form that depend on basically n Riemann invariant, which satisfies the usual diagonal relationship where lambda is the characteristic speed, and this is the semi-Hamiltonian property. Okay, and the whole point is that we managed to show that this chain is integrable, and the point is that, to the best of our knowledge, we have not found that chain anywhere else. So this looks like a novel example of integrable hydrodynamic chain. And more than that, hydrodynamic chains have been cataloged, if you want, by Odesky and Sokolov. I don't remember the year. And apparently, it doesn't look like our chain belongs to that classification. And probably that's because we have two seeds, which, as I was mentioning, is sort of weird. So I almost made it in time. Long story short, we have two very different examples of matrix ensembles. And though the way we treat them is very similar, what we find is actually very different, because the HME can be written in terms, the continuum limit of the HME can be written just in terms of one PDE per time, while here we have an infinite chain of PDEs for the SME for each time. In the case of the HME, its structure allowed us to see a novel type of phase transition, which is signaled by dispersive shockwaves that propagates in the space of thermodynamic parameters. While for the SME, we saw something quite different. That is, we saw this novel chain of PDEs, which is integrable in the sense of hydrodynamic reductions. And I guess I'm going to stop here. Thank you.
Thank you, Costanza. Questions? Could you show again how your U's are related to the W's in the?
Do you mean these ones?
Yeah.
So I was curious how you produce the plots of these oscillatory
Phenomena. Well, easy answer with Mathematica. So basically, this is just, you fix T2 and T4, and you go here, and you just plug T2 and T4 here, and this is the recursive solution. Of course, the first few values you have to calculate numerically the integral to have your starting point, because it's a recursion. So you need the first two values, and Mathematica is going to do that for you. But then once that you have that to a reasonable level of accuracy, then it's just a matter of implementing this recursive relation. Of course, in that plot, everything is rescaled to be consistent with the rescaling that you have with the cubic.
And so related question.
Yeah.
In the symmetric case.
Yes.
Will there be shocks? Is that known? And are there numerical simulations
So
that show the oscillations?
That's not known. That's something that we'd like to know. I would be surprised if we didn't see anything similar, though. This is here you have a chain, so each PDE depends on the other. But I've been talking with some colleagues on how to go about and try and simulate that, because that would be something that would be very interesting. Of course, we need to understand how to deal with the fact that we have infinitely many fields, so we'll probably need to truncate it somewhere. But that's something that we're thinking about. Thank you.
Do I have time for one short question? If there is any, let me go check if there is any online. I don't think there is any. Oh, yeah, there might be something. So I can read it out.
Sure.
How should, this is a question from Panos Kerakidis, how should one think of the DSW at the level of the phase transitions, including the fixing of T2, T4, and varying T6 alone?
So I'm not sure I understand the question, but the point is that depending on where you are with T2, T4, and T6, you're going to either have a shock or not have it. And the point is that Well, first of all, let me go back here. If you look at this cubic, the parameters here depend on the times. So depending on the values that you have, you might be either in a multi-valued case for your cubic, or you might not be in a multi-valued case for your cubic. And of course, you have the transitions once that you go through the gradient catastrophe. So you move basically from a situation like this to a situation like this. And then if you keep evolving, you get something like that. And given the question, I would also like to mention that the way the shock looks and whether there is a shock depends really a lot on the signs of these coefficients. So we've chosen here this example because it looks particularly nice. But if you go in another region of the, let me go there, of the thermodynamic, of the space of thermodynamic parameters, you can see shocks that look a bit less weird than the one that we had before, if you want. And there are regions where you don't have a shock, where we would expect a shock just based on the equations. But I'm not going to go into that. But the point is that it all depends on the signs of the cubic that we had before, if I can find it somewhere. So it all depends on the signs of this cubic, of the parameter, of the coefficients of this cubic, basically.
Panos, feel free to unmute yourself if
Yeah, sure.
you would like to.
I'm not, because I'm not sure that I actually
further
answered his
comment.
question.
Well, I was more like thinking in terms of like thermodynamic quantities that you can measure.
Yeah.
How can you interpret the dispersive shock wave at the level of thermodynamic quantities? You take derivatives of the partition function with respect to different things like the temperature, the chemical potential, and so on and so forth. How do we interpret the shock in that kind of context?
That's actually a very, very, very good question. That's something that we're trying to work out right now, because the point is that this is at the level of this specific ratio of taus, which is not necessarily related to a specific thermodynamic quantity like the expectation of the trace of m squared or something like that. And indeed, that's what another thing that we're trying to do now is to understand what happens when we're going through the shock to those, to those observables, basically. But that's something that we're still working on.
Thank you.
Yeah.
That's always good when you have co-authors in the room that can say things way better than you.
Yes, it does. So, no, I think in relation to this question, so the potential U can be interpreted as a second discrete derivative of the partition function, and X is related to the size of the system. So the random matrix model is equivalent to a Coulomb gas. And you think that when you increase X, you increase the size of the system. So U is can be interpreted as the susceptibility of the chemical potential. So that would be the physical interpretation.
Okay, thank you very much. Let's thank Costanza and all the speakers at the first part. We have a coffee break and a photo outside. I don't know which order.
Well, we have the choice to photo outside or inside.
Oh, okay.
So, and Barbara, you have anything?